Okay, so I think that we should start the lesson for today. For today's the topic would be training neural network, part one. So we have two parts. Part one is for today, and part two is for the next week. For today, we will discuss about activation function, data pre-processing mechanism, weight initialization, and normalization mechanism. First, we discuss the activation function. In the slide, you can see several activation functions that you might use when working with neural network. We have discussed about sigmoid function, time function, ReLU function, right, and Leakey ReLU function, right? So some newer activation function that you can use today in the popular deep learning framework such as in PyTorch and TensorFlow. Okay, so first we discussed further a little bit about the sigmoid function. So the sigmoid function can output the number in the range from 0 to 1, right? So for any input from infinitive negative to infinitive positive, we have the output in the range of 0 and 1, right? And this is the set of the sigmoid function, right? And in the past, the sigmoid function are widely used with the neural network because they simulate the firing rate of the neuron, right? And it have a very nice mathematical representation. For example, this is a formula for the sigmoid function, right? And it also have very nice representation for the derivative, right? So the derivative of the sigmoid is, represented by itself. So it's very easy to calculate, right? However, there are three downsides of using the sigmoid function as the activation function in the neural network. So first thing we are discussing here is about the vanishing gradient problem due to the saturated neuron. So you see in the shape of the sigmoid function, it has the following shape, right? So if we have a very big input or very small input, then you see the sigmoid function will always output 1, right? 1 or 0. And and at this point, you see the curve of the sigmoid function here is flat, so the derivative is 0, right? And if the derivative of the sigmoid function becomes 0, then you see on the way we updating the weight in the sigmoid, the weight in the neural network, we have to we have the mathematical function to update the sigmoid as the weight is to be the weight at this moment equal to the weight of the previous moment step, and then plus with the learning rate multiplied with the gradient, right? So if the gradient becomes 0, then we have no update to the weight, right? So that's the problem with the saturated neuron. So you see, this is that's a clearer example of the sigmoid function with different input. For example, here I have the question: what happens when the x equal to -10? So it is -10. Then you see the sigmoid here will output 0. if it equal to 10, then also the sigmoid will output 1, right? And this is the curve for the derivative of sigmoid. See? Then if x equal to 10 or minus 10, then the derivative equal to 0. When x equal to 0, here we have the sigmoid will output I mean 0.5. Okay, this is a mathematical formulation for the derivative of sigmoid. Okay, so besides the vanishing gradient problem, if we use the sigmoid as the activation function, we have another downside. The output average is non-zero. So what do I mean by the output average is non-zero? You can see here that the output of the sigmoid function is always, positive from 0 to 1. So if you have a lot of input and a lot of sample that push into the sigmoid function, then you see the average output is of course non-zero, because the output is from 0 to 1. This is always at the positive side. Okay, so this is the example in detail. For example, this is a net input, right? The weighted sum of every input and the bias, and then the activation function, right? And now we discuss about what if all the neuron input xi are positive, right? Do you have the answer for this question? So you can see that if all the neuron inputs xi are positive, right? Then how about the gradient of the objective function with respect to w? Do you have the answer for this? So you see, this is a set of the derivative of the sigmoid function is always, positive, right? Then of course, if you have this case, then all the elements of W will have the same sign as the derivative of F. Then in this case, it's the same negative or the same positive, right? Is it correct? Is it a correct statement?
Yeah, I think it's clear.
Sorry? Do you think it's the correct statement?
Yes, it's correct.
Okay. Then in this case, you can see the consequence. The gradient can only be vectored in certain dimension in the search space, right? So we have the third downside. The calculation for the sigmoid function is we have the exponential operation in here. So the calculation is a little bit expensive, right? So now we discuss the time function. For the time function, you have the output is in the range from -1 to 1. So in this case, you have the average output is 0, right? because the output is from -1 to 1, so the average output is 0, but it still suffer from saturated neuron, and then that's the problem of vanishing gradient. So if the input is very big, or if the input is very small, negative small, then you get the vanishing gradient problem. Okay, so now move to the ReLU function. So the mathematical formulation for the ReLU function is very simple. If you have the function equal to a Mach of 0 and x, right? So if x is less than 0, then the output is 0, and if x is bigger than 0, then the output of the ReLU function will be x. Okay. So for the ReLU function, they have the following property. You have no saturation in the positive region. Saturation mean the position where the output is so flat, right? And then the derivative becomes 0, right? In this case, you have no saturation, right? It's very efficient in terms of computation because the function is very simple, either 0 or x, right? In the case of time or the sigmoid function, the calculation includes the exponential operation, and that is correct. Okay. Yes. Another advantage of using the ReLU function is, in practice, is converge faster than sigmoid and time function, and by experimentation, they observe that the speed is 6 times faster. Okay. However, the ReLU also have two downsides. First is non-zero average output, right? And the second downside is the problem we will discuss here. So first, let's take a look into this example. We have the ReLU activation function in here, right? And now we try to understand what happened when x equal to -10. What will happen when x equal to -10? What will happen when x equal to 10? And what will happen when x equal to 0? So when x equal to -10, then we see here the output is 0, right? And what? And in that case, we have the gradient of the value equal to 0, right? When the x equal to 10, then okay, it's fine. When x equal to 0, do we have the, actually it's I mean in here, I mean practically, I mean the gradient equal to 0 is practical, but mathematically is have no derivation at that point, right? Because it's non-contiguous in terms of derivation. Okay, so because for the value function, you have the, when the input is negative, then the output is 0, and in that case, use people saying that the value are thrown out due to the data set that makes the output being always negative. And because the output being always negative, then the variance becomes 0, and that neuron will not be, that weight will never be updated again. And in that case, people saying that we have dead value or dying value, right? So this is a visualization for the data cloud input. I mean, for the data cloud sample, you will see that for some input that makes the ReLU output negative, then in that case, I mean, that value will be never be updated again. But in some part of the sample, you got the active value, right? So usually, in order to reduce the dying value effect, we can initialize the value neuron with a small positive bias, right? The bias will be used in that function in here. It is to make sure that, okay, somehow we can reduce the possibility of observing the negative output, right? Okay. So here we have the extension of the ReLU function. We name it Lecky ReLU, and it is a formulation for the Lecky ReLU. You have the max over 0.01x and x. This is that parameter, right? And this part make the negative part of the value, I mean, become not becoming 0, right? So in that case, you see the function here, they are not saturated, even when it is small or x is positive, right? And you still have the computation efficiency value function, because here the mathematical is so simple, even for the derivative is so simple, right? And it still have the conversion rate much faster than sigmoid time function in practice. Somehow it's about 6 times faster in practice, and it will not die because you have no, I mean, vanishing variant problem. You have all the extension of value is called parametric rectifier unit, and this is the mathematical formulation for the Lecky, and it is a mathematical formulation for the parametric rectifier. So for the Lecky value, it is somehow a constant, right? And for the parametric rectifier, you have the alpha as the hyperparameter that can be learned during the learning of the neural network, right? So in this case, you don't fix alpha, but alpha is a learning parameter. Okay, and it have the advantages of this value function. It's not saturated. It is computationally efficient. It's also converts much faster than sigmoid, and it will not die. Somehow the computation for this is the cost higher than for the Lecky ReLU and higher for the ReLU function. We also have the exponential linear unit, and this is a formulation for the ReLU function. It will equal to x if x is positive, and equal to alpha exponential x minus 1 if x is 0 and 0 or negative, right? And it has the zero byte as the computation is a little bit expensive because it requires the exponential power. It has benefit of value close to zero mean output. Okay, negative saturation. So in that ALU function, you see that you got the saturation at some point when the input H is too small, right? And you get the the neuron saturation, and actually at that point you see the vanishing gradient problem. But somehow in practice people saying that that might become the advantages, and because they having some negative saturation can add some robustness to noises input for the model. If we zeroize the value function, parametric value, and exponential linear unit, we have the max-out function. And in that max-out function, you have the following mathematical formulation. It has two parts, one for the left and one for the right. And this function does not have the basic form of dot product, right? And it does not saturate, does not die. And but you have double the number of parameters per neuron. You see. Do I have any question? Okay, so let me conclude with the last slide. Okay, last two slides in the activation part, and then we can have question session. So in practice, people nowadays use a lot of ReLU activation function, especially when you are dealing with the convolution neuron network, dealing with the image data type, right? And however, for the ReLU function, you should be careful with the learning rate, because for the ReLU you got the the death value problem, right? So if somehow if the net input become negative, then okay, the gradient becomes zero, then that weight will not be updated anymore. And so that case, you should try to not use a you should try not to use big learning rate, because with big learning rate, maybe after the update, after the stack, then you might end up into NetD region for the ReLU. Okay, you might try out the Leakey ReLU, mark out ReLU as a real function, and somehow they can boost the performance of the network, but not in every case. So this is just a suggestion that you might try out, right? Don't use sigmoid all the time. This is just a suggestion in especially for the image processing. Then the ReLU is very very powerful in compared to sigmoid time function. But in some situation, in some specific data sets, people still using the sigmoid time for specific problem, especially for example in using the neural network for reinforcement learning. So I myself have a experiment with a different activation function, and I'm seeing that for that reinforcement learning test, the tank of the sigmoid somehow perform better than the ReLU and ReLU relative function. Some new activation function that you might try, for example, the ReLU 6. Actually, it have the mean of SIG and the ReLU. That somehow you cap the maximum output of the ReLU to be SIG, right? SIG is that's the number choosing after the experimentation, okay? And you can have switch and miss to test. Here the shape of different activation function. For example, we have the miss function somewhere here, and okay, the sigmoid somewhere here. Okay. Okay, so do I have any question regarding the part about the using of activation function? Any questions so far?
I have a question.
Yes.
Can you explain about the zigzag path in the sigmoid function?
In the sigmoid function.
The zigzag path.
Okay. So you see that in the sigmoid function in here, we have the problem that this is, for example, this is a formulation for the derivative, right, of the loss over the weight W, and this is as the the derivation, right, of the sigmoid, right, and this is x, and then this is a upstream gradient. So we see that for the sigmoid function in here, you are seeing that the part is positive, right? Let me have my pen. Oh, okay, I have my pen already. So this is positive, right? And you are seeing that if this one is positive, right, and then you see the the sign of that derivation will have the same sign as x, right? And if you have the data set is always at the positive sign, and if for example, here is the annotation for the input and the training data. If you have always the if the input is always positive, for example, right, then the update of the gradient will be always into that direction. Of course, because it is updation after the step, so you don't go, go to the optimal direction here, but you go a little bit in the zigzag way. It's always into the region, right? You never go to the other, because you have that specific problem of the constraint between the side of the input and the side of the side the derivation. Is that clear?
Okay, thank you.
Is that clear?
Yeah, I think it's clear.
Okay, maybe I will try to explain to you how to say. So let me explain to you again. So this is a formulation for the, for the derivative of the loss over the weight, and this is a formulation. Is it clear? Is this clear, this formulation? Let me clear the drawing. Do you still seeing my slide?
Yes.
Yes. So is this clear about the formulation for calculating the derivative of loss over the specific weight W? Is it clear?
Why is it 1 minus sigma here?
How about this one?
1 minus the function 1 minus sigma.
Because this
Why?
is a derivation of the sigmoid function. So the derivation of the sigmoid function.
Okay.
This one. You see?
Yeah, yes.
Okay. So this part is always positive, right? Right. And
Yes.
this is the upstream gradient, right? The upstream gradient is calculated is the same way. Is it clear?
Yes.
So in this case, you see the sign of this output will have the same sign as x. Is it clear?
Yes.
If x is positive, then okay, this is positive. If x is negative, then this one is negative, right?
Yeah.
In the case for the input, you have always positive input. Is it clear? Assume that you have x is always positive.
Yes, it's clear.
Then it is always have that to be positive also. So it's always going this way. It cannot going to be smaller this way. I mean, this is just a problem that you can go in every direction of the subspace. You have the constraint that, you know, this is always explore the positive regime, and it have no trend to explore the negative regime because it is constrained by the size of the input data. And I mean, this problem might happen, right? Might happen if you have the, for example, the AKS is always somehow positive or always negative, right?
Yes, I think I got it.
Okay. Do I have any question? Okay, and if not, then I think that we can have break for 5 minutes, and we will continue. Do you still seeing my slide?
I think you haven't shared your screen.
Sorry?
We don't see your slide.
Okay. Right. So do you see it now?
Yes. It's okay.
Okay, so I just update the slide a little bit. I do add the formulation for updating the weight if you somehow I mean you somehow forget about this function. So this is a formulation for the loss calculation. So the the arrow senior over the specific weight, right? And this is the update function for the weight in every step. So actually you have the weight of this step equal to the weight of the previous step minus the learning rate and then the delta loss, right? Because the delta loss in our case here is always positive, for example, because the XI is always positive, right? So in this case, you are seeing that you are always updating the weight to be always smaller, 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 right? And in the other way, you always updating the weight to be bigger, 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 and bigger, right? And that's the reason we are saying here that the gradient can only be directed in a certain dimension in the subspace. It can go to the other part of the subspace. Is that clearer? Some of you are saying that when you are learning, right, you're trying to finding the weight after, in the iteration, right? In this case, in this situation, you're always trying to find the W become always smaller, 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 right? And every, way to be smaller, smaller, smaller. Is that the right way to find the optimal weight? No, right? Is that clear? That not in that case, because you are that searching the optimal weight become always smaller than the weight in the initial step. So you don't go the other side of the search. For example, maybe the optimal weight is to be bigger, for example. Is that clear?
Yes, it's clear.
Okay. Okay, so now we can move on to the next part. Data pre-processing. So you are seeing in this slide, we had the problem of, always positive data that may cause problem for the sigmoid activation function, right? If we have the input X to be somehow not always positive, not always negative, we have zero center data, like the balance between the positive and negative, then you may have no problem like this, right? So now about the data pre-processing, right? Data pre-processing is a process of transforming the data distribution to zero mean. Usually we want zero mean, right? By zero mean, we can subtract all the data sample for the sample mean. For example, here's the original data we have, right? It's like this. It's not zero mean. It's, for example, for the X, the mean would be somewhere in here, right? The mean. We can zero mean, zero center the data to have the data center around the origin of the axis, right? And in order to do this, we can minus the sample to the sample mean, right? And we also can do further by normalize the data to have a standard deviation equal to 1, right? So that we can divide x by standard deviation to, reduce the scale of the data to be around unit. Okay. Right, and by doing this, recenter the data, we can, we can avoid this, somehow reduce the probability of observing the side effect, the probability of observing the side effect. Okay. Okay, so yes. In reality, beside zero center data and normalized data, we also want to, decorrelate the data. For example, here we have the original data that have the somehow the correlation between the x and the y. X, y is two features of the data, for example, and you see that they have the correlation, linear correlation between x and y. X in 3 is 3, x is like a linear function of, sorry, y is like a linear function over x, right? And we want to remove the correlation of the data because we don't want to, we want to reduce noise and maybe reduce the redundant feature on the data. So we can decorrelate by using the principal component analysis, right, to have data to be to have decorrelated data. And you see, if we transform the data from this dimension to this dimension, we are seeing that there are no, correlation between x and y anymore. Okay. And we, of course, can widen length data to have the data to be centered around visual. I believe I have the notebook for you to practice. Okay. So in practice for image, you can only, sorry, you should do center only. You don't need somehow PCA or data whitening. You can just, try to zero mean the data only. For example, people are doing experiment with the CIFAR-10 data sets, and for the ANDNet, they try to subtract the sample with the mean image. So the mean image is, the image has the same size, and every pixel is a average over the pixel of every sample, right? For the VZZNet, they subtract the mean, but the mean is calculated for each channel. Okay, so for example, you have 3 channels, then you have 3 number for 3 channels. Okay, to subtract the sample. Or you can do the subtract per channel mean and divide by per channel standard deviation. So now you want to have a normalized data, right? And this is a mechanism used in the ResNet architecture. Often you rarely use the PCA or whitening, right? This is for the image, but for other type data, you may see the PCA is an useful mechanism to decorrelate the data. Okay, so this is the demo for you. I think that you might open that notebook and try to see it by yourself about the data pre-processing mechanism. I we'll give you 15 minutes to have a look into that notebook and try to understand what they are doing. Okay. Okay, so let's try to open the notebook. Um, Are you done? Hello. Hello, hello. Okay. So maybe we need more minutes for everybody, right? Okay, so I think that we should continue because the lesson is quite long for today. Do you still seeing my screen?
Yes.
Okay, so now we discuss about weight initialization. Weight initialization is things you would do at the beginning of the training step. Sorry, not training step, but the training process, right? Remember about, I mean, every weight is updated uh, by the function of the pivot weight, sorry, by the weight of the pivot step, and then the arrow senior, right? So at the beginning, you should initialize the weight, and the way you initialize the weight might impact the performance of the model at the end. First, we discuss about the initialization of the weight to be 0 at every neuron. Then do you think what will happen in this situation? What is the problem with this initialization setting? Maybe I should ask one of you. Kiều Trọng Thanh, according to your view, what is the problem with this initialization? Hello. I hear noise, right?
Can you hear me?
Yes. You are saying that the output will be 0 and there will be no gradient. This is not correct because for the activation function, not every activation function has the gradient equal to 0 where the input is 0. For example, for the sigmoid function, right, the gradient would be 0.5 if the net input is 0. Is there anyone that want to discuss about this problem? What if the weight are initialized to be 0? And the answer is every neuron will learn the same feature in iteration because they act the same, right? The net input are the same, right? The arrow senior are the same, so the weight are updated with the same amount, and so that every neuron will learn the same thing in iteration. And this is a thing that you want to avoid. You want each neuron to learn something different from the other neuron, right? So that they can cooperate and then produce the right model. Okay, right. Okay, so first thing to remember that you should not initialize the weight to be all 0 or to be all the same value, right? If you have the same value, then you got the same problem. Every neuron will learn the same thing. Okay. And now the second idea is to initialize the weight with a small random number. I mean the random number may be generated from the Gaussian with zero mean and I mean a small standard deviation, for example. For example, this is the way you initialize the weight W, and it look okay, right, in the beginning. For small network, this could be an acceptable initialization. You will have no problem with for small network. But in the case of a deeper network, then you might got the problem. This is a visualization for a small random number, right? You start, in this implementation, we have 7 as well as 6 layer, and this is the output after the first layer, the second, the third, the fourth, the fifth, and then the sixth, right? And you see, you just visualize the output after each layer, right? So you see, for when you visualize the higher layer, then you see the mean equal to 0, but the standard deviation becomes small and smaller, right? And for this, what is the problem? How about the gradient? The gradient is calculated this way, right? This is the gradient of a specific weight equal to this is the learning. Sorry, this is not what is the alpha. This is the loss here, right? And this is the learning rate. This okay. This is learning rate. Yes, it's alpha. Sorry, this is sorry, I somehow could not understand about this. Upstream gradient. So this is arrow here, and this is a derivative. And what's about this one? So this is just the formulation for calculating the arrow here from for each layer. Layer number L is equal to derivative of the activation function, and then you multiply with the arrow here at the upper layer, right? And then this is the weight at the upper layer, right? So actually you are saying this multiplication because the derivative of the sigma function here is all way from 0 to 0.5. So you see that the arrow here will be diminished, right? And in this case, if L become lost for big L, then the arrow here will be come smaller, right? And somehow it will become 0, right? And in that case, you have no learning because the variance become 0. Is that clear in this slide? Is it clear? Do you understand the formulation? Okay, so I might continue. So this is a situation when we have, small, in the case we can initialize the standard deviation to be a bigger value. In the previous situation, we had started with small standard deviation, and that small number we make that plus the small gradient make that to be 0 for big L, and now we try to increase that to be bigger number. Okay, and you got the same situation. The gradient is always will become 0 in a higher layer, and in this case you see at every layer you see gradient become 0 because the output is somehow on the left, on the right. This is a same formulation for calculating the delta loss. Right? All the activation in here will become saturated, right? So there's one research about making the right initialization for the weight, and they propose this scheme to initialize the weight, and the name for the initialization is Xavier initialization. It's named, following the name of the author. So now we discuss about the Xavier initialization. Assume that X and W are independent and identically digital random number, and the mean are 0. And you see this is a calculation in the forward direction. The variance of y equal to variance of, this is a formulation for y. W1 is 1, and then Wn is n plus bias, right? And the variance of Wi xi equal to, this is the formulation for calculating the variation. Okay, so I'm not going into detail into this. So in that case, the variance y will equal to n multiplied with the variance of Wi and variance of xi. Okay, because the expectation here is 0, because the data we assume x and w are 0 mean. Okay, is 0 mean. Okay, so assume that we want we want to have no changing in terms of variation between the x and so between y and x, but y is the output. At the next at that neural net at that layer, right? We want no changing of the variant, because you see the problem of changing the variation in here, and it gets the output to be 0, right? We want to keep the same shape for every layer into a nice shape like this. We don't want the standard variation to be smaller, right? We want them to be the same, right? So in that case, this, I mean, computation should be 1, and in that case we want the variance of Wi equal to 1 divided by n, and this number of dimension, right? So the same goes for the backward variance in the string, and the variation of Wi equal to 1 minus 1 over n out the number of dimension. So by average, we can see that it is good to have the variance of Wi equal to 2 divide the number of input dimension and output dimension. And that is the idea about the Savie initialization. So this is a experiment with Savie initialization. You initialize the standard deviation to be 1 over square input dimension, and it is a formulation for W, and by doing like this, you see the output of the bit of every layer to have very nice bell shape, right? Okay, so the same goes for time to value activation function. So this is the calculation for the variation of Y, I mean the output after a layer, and X is the input, right? And then you can see the variation of Y will equal to number of input dimension, half of number of input dimension divided by 2, and then multiply with variance of Wi, multiply with variance of Hi, right? I mean, if you want to have the detail proof about that function, you might take a look into that paper. But to be easy understanding, you might think that for the value function, because it has this shape, and you can see that it is deactivated in a half of the scale, so that you divide by 2. Okay, and then for the value function, you can initialize the weight to have the variance of 2 over number of input dimension. If you are doing like this, to do the initialization for the output of the object layer, you see there no vanishing of the gradient of the layer. This is for another initialization scheme. It's called HE or MSRA initialization, and actually in this case you are initialize with this standard deviation. Sorry, somehow I misunderstood the figure. In this case, you see the changing in terms of variation with how nice initialization scheme, right? It becomes smaller, and then it's very small at the last layer, right? And in this case, when you correct with the value with the right initialization, you see there's no, diminish in the layer. Do I have any question? Any question? Okay, so now we discussed about normalization. First, about batch normalization. We want the activation function to have an output distribution with zero mean and unit standard deviation. Right, this somehow we want. Why do we want to have output distribution with zero mean and unit standard deviation? Because we want to force, the output of every layer to have a very nice bell shape like this, for example. Right. So what we can do is to force the transformation with that idea. So this is the output after the activation function, and what we can do is to subtract the output with the mean, and then we divide by the standard deviation, and then we got the new output. And for the new output here we have unit standard deviation, okay, and zero mean. The idea of zero expectation unit standard deviation is two types. For example, it might cause the model to be underfitting. So we can loosen the model a little bit by create an exit for the model if it does not want to be bound by the by the way we normalize it to be unit deviation. And if we doing like this, the population for the batch normalization will be like this. The y, this is the unit standard deviation, right? And we can modify a little bit, and now the new output will be y equal to the output multiplied with the gamma and plus beta, right? And the gamma and beta here can be considered as the learnable scale and shift parameter. We want to scale the output to not be zero, to not be unit standard deviation, but to have this deviation, and we shift it to an amount of beta, and we let the model to learn the gamma and beta during the training, right? If the model decides that standard unit deviation is the right way to do, then in that case it might learn gamma equal to sigma and beta equal to mu, and in that case we have the zero expectation and unit standard deviation. Any question about this batch normalization mechanism? Do you have any question, or is it too simple for you guys? So this is just an example of calculating the batch normalization for the init data. You have the input data have the following dimension and the dimension. We can calculate the per channel mean and the mean per channel, right? And then the per channel variant, and then we can normalize it. Right? And after the normalization, the shape of the data is the same and the dimension. Any question? Okay. Right. So the batch normalization, I mean, you estimate the mean and variance. I mean, depend on the batch in training, right? But in testing, you can do this at the test time, right? So how do you evaluate the model with batch normalization in that time, at that time? Do you have any idea? Any idea? So what you can do is to, I mean, calculate the mu and the sigma by the average of the value seen during the training. So this can be the average of every, I mean, mean during training, and this is average of every, I mean, standard deviation during training. And then as the testing, you can that using this mu and sigma to, I mean, transform the, I mean, to transform the output, right? So we have here we discuss the batch normalization for convolutional network, and in this case we have a spatial batch normalization. In a fully connected network, you have this is a shape of the input dimension. Then in this case, the mu and the sigma will have this shape, 1 and d dimension, and the gamma beta will have this shape, right? And then this is the output y. For convolution neural network, you have that specific channel, I mean the channel parameter. So the dimension is equal to, I mean, it is the number of sample in the batch, it is the number of channel, it is the height, and it is the width of the image, right? So in this case, you can have the mu with this configuration, the gamma beta with this confirmation, and that will be the formulation for calculating mu y. Okay. So usually for the batch normalization, it is inserted after fully connected layer or convolution layer, and of course before the non-linearity, before the activation function. For example, here is one example. You have the fully connected layer, and then the batch normalization, and then the activation function, and then the fully connected layer, batch normalization, and then activation function, right? Because for the activation function, you see some activation function will not work well with, I mean, non-zero input, non-zero center input, right? Okay, so the pro and con of batch normalization is like this. The pro, it can make the deep network much easier to train because you force the output at every layer to be normalized, right? So that it can be easier to train. It improves the gradient flow. You see the problem we have, I mean, when we have the problem when with deep layer, like in this example, right? So what if you have batch normalization, then we can force the output at that layer to be, I mean, have a very nice set, right? Yes, it's allow higher learning rate, faster conversion, right? Because now you have more flexibility to choose the learning rate, right? The network become more robust to initialization, right? Because you force, I mean, you add the batch normalization, I mean, in between the net input and the non-linear, the activation function. Right? And it can be some kind of regularization during the training. Because when you do the batch normalization, you actually recalibrate the input by using the calibrate the input at every input by considering the other input in the batch. So it have the regularization effect, right? You have zero overhead at test time because you can use the mean and the standard deviation calculate during the training time, right? According in that scale, you make sure that characteristic of the test should not be very different from the characteristic of the training data. The disadvantage of batch normalization is somehow in some situation that you might see the model behave differently during training and testing, and it could be a common source of bugs for the model, because choosing this the value will work if there's no differences in terms of the characteristic of the training and the test data. But if there's big differences, then you might got the problem. We have variants of batch normalization, such as layer normalization. So in batch normalization, we normalize over batch, and for layer normalization, we normalize over the dimension, right? The n is the number of sample in the batch. It is the number of dimension of the data. Here we normalize over the batch, and for layer normalization, we normalize over the dimension. Okay. And for convolutional neural network, it is polymerized the spatial batch normalization, and here we can do instant normalization, right? And we in that case we did the set for the mu and sigma, right? If you compare different type of normalization, you can see that for batch normalization, you do the normalization over n sample of the batch, right? And for the layer normalization, you do the normalization for each sample, but on every channel, right? And it is the normalization. You do the normalization for each sample and in each channel. Group normalization is that something in between. You do the normalization for one sample on I mean a subset of the channel you want. Okay, do I have any question for this part? Any question? I think that I'm going a little bit too fast, so we still have time to discuss about I mean the lesson if you wish. Any question? Hello. Okay, so you say that you have a question, need more time at home to fully understand, right? So I suggest that you take a look into the course at Stanford and the references in the material folder and the thing I put in here to fully understand the thing we discussed today. So if you have no question, then we can stop early today. Do I have any question? Hello. Okay, then I think that we can stop early and looking to see you in the next week. Bye bye.